Hi, welcome to Mathematical Induction, Module 4 of the University of Sydney's up to Extension 1 Mathematics Bridging course. My name is Alan and I'm one of the teachers in the Mathematics Learning Centre. You may have seen things like the sum of the first 3 integers is 6, or that the sum of the first 7 integers is 28. In fact, you might think that the sum of the first n integers is given by this formula. But how would you prove this? How could you prove this? There are countably infinite integers, and so it isn't feasible to check that this proposition holds for each integer above 0, as we haven't got an infinite amount of time on our hands to check each and every one of these infinite cases. So this begs the question, how could we possibly justify such seemingly impossible statements? Well, we actually use a property of the integers. In particular, for every integer, there is a next and larger integer, namely that integer plus 1. In the next 2 videos in this module, we will learn about a specific proof technique known as mathematical induction. Mathematical induction allows us to prove or disprove a very specific type of statement that depends on all the integers beyond some base integer, which you can think of as the starting point for the mathematical induction. Proving a statement using mathematical induction requires you to justify 2 claims in order to conclude a third, which is the thing that you're trying to prove. Before we dive deep into the videos about mathematical induction, let's explore some analogies related to this topic. There are many analogies for mathematical induction and why it works, but today I will describe one that involves an infinitely tall ladder. Imagine that you had a ladder with an infinite number of identical and evenly spaced rungs, and that you could step onto some rung of this ladder. If, in addition, you knew how to move from one arbitrary rung to the next, then it's not hard to see that you could climb up the ladder as high as you'd wish above the starting rung. Here's an important thing to note about this analogy. We can only guarantee that we can climb arbitrarily high above the starting rung if we can get onto some starting rung to begin with. If we can't get onto any rung, then even if we could climb from one rung to the next, we can't guarantee that we can climb the ladder as high as we want to. Another important thing to note is that we don't need to start on the first rung. Maybe you're tall or a good jumper and can start at the 5th or even the 14th rung. Just so long as we can get onto some rung and move from one rung to the next, then this process of climbing as high as we want to will work. Next, we need to step back and note our assumption. We have only assumed that we can move up the ladder from one arbitrary rung to the next. There's no notion of going back down the ladder. You essentially can't get off it. If this were reality, then maybe you shouldn't get on this ladder without the extra condition that you can move back down the rungs. But remember, in mathematical induction, this doesn't matter, and we only move forwards and not backwards. So, to reiterate, in mathematical induction, we have 2 claims to justify. Number 1, we need to be able to start somewhere, or on some rung of the ladder. And number 2, you need to be able to move from one step to the next, or from one rung to the next. If you can justify these 2 claims, then it's guaranteed that you can climb as high up the ladder as you'd like. Remember, the rungs are identically spaced, and so moving from one rung to the next is therefore the same process no matter where you are on this infinitely tall ladder. There are other analogies to the process of mathematical induction. Some people liken this to falling dominoes. Let's say you have an infinite set of dominoes. If these dominoes are evenly spaced, such that if one falls, then so does the next, and the one after that, and so forth. And if we can choose a starting domino to begin the cascade and then knock it down, then it's clear that all the dominoes beyond this starting domino will eventually topple. It might take an infinite amount of time, but they will eventually topple. As a third and final analogy, you can imagine a chain of implications that starts somewhere and extends ad infinitum. Don't worry too much if none of this makes any sense. The reasoning will be explained in detail by our guide Clinton, who, in the next video, will illustrate the method of mathematical induction, both in general and then using examples. He'll run through several proofs that use mathematical induction as their justification. I hope you enjoy this module, and don't forget to practice the exercises in order to get the most out of your learning. Best of luck.